Hi everyone, we're starting part B of our module on exercise at altitude. We ended the last section or part A on this slide. So again, this slide shows the relationship between barometric pressure and the change in the partial pressure of O2 such that when you increase in altitude, you decrease the barometric pressure and you decrease the partial pressure of O2, which is the driving force to get oxygen in the body. So at altitude, you have compromised gas exchange, O2 transport, because the hemoglobin is not fully loaded, and reduced oxygen at the muscle cell, which compromises aerobic performance. There are three environmental conditions that I want to explore at altitude. One is air temperature, humidity, and solar radiation. So air temperature typically decreases as altitude increases. So cold air can hold little water, so the air at altitude is really dry. These two factors combine to increase the susceptibility to cold-related disorders and dehydration. The air temperature at altitude typically decreases 1 degree Celsius for every 150 meters of ascent. So with that in mind, what is the decrease in temperature at 3,000 meters? Well, 3,000 meters divided by 150 meters is 20. So that would mean a change in temperature by 20 degrees Celsius if you went up to 3,000 meters. This contributes, as I mentioned, to the risk of cold-related disorder. Second of all, humidity plays a factor at altitude. That the cold air holds very little water. So air at altitude is very cold and very dry. So we have dry air, which leads to quicker dehydration through the skin and the lungs because it's evaporated so quickly. When completing my doctoral work, I was a professional cyclist. As you know, I've shared that with you before. And I remember competing in a multi-day stage race at altitude. This was over 6 days. And one day, I didn't even know I was sweating much, and I significantly dehydrated. I ended up having heat exhaustion and riding into the ditch. So needless to say, I had to go to the hospital and get an IV bag to recover. And anyways, this was very ironic because my PhD was funded by the Gatorade Sports Science Institute on a lot of work looking at muscle metabolism and dehydration, and yet I myself was getting dehydrated. And the key message here is that at altitude, you don't even know you're sweating because the air is so dry that when sweat gets on the surface of your skin, it's wicked away, it's evaporated right away because the air is so dry, and so it evaporates very quickly. Next, I want to talk about solar radiation. It actually is increased at high altitude. And this is because the atmosphere is thinner and drier at altitude. So solar radiation is more intense at higher elevations. So you can get a sunburn a lot quicker. The effect is magnitude when the ground is snow covered, because what you see is the snow reflects and amplifies the solar radiation. So you have a higher risk of getting UV burn and therefore a sunburn. Here's a summary of what we've covered so far. So really altitude presents a hypobaric environment. Altitudes anywhere at 1,500 meters or higher have a notable physiological impact on exercise performance. Although the percentages of gases in the air that we breathe remain constant, the partial pressure of each of these gases decrease with the decreased barometric pressure at higher altitudes. So that low partial pressure of oxygen in the air at altitude is the environmental condition with the most profound physiological impact. Because the partial pressure in the lungs is low, the partial pressure gradients between the alveoli of the lungs and the blood, and between the blood and the tissues, is decreased. Again, we just mentioned that air temperature decreases as we increase altitude, leading to more susceptibility of cold-induced issues. And then we also have a higher risk of dehydration as well as getting a sunburn due to solar radiation being higher at altitude. Now we're going to discuss the physiological responses to acute altitude exposure. So the first thing you'll really notice upon arriving to altitude is your ventilation increases immediately. And I've noticed this as soon as I touch down at altitude, is that you're ventilating more frequently. So this occurs at rest and during submaximal exercise, but not at maximal exercise. Really what it is the decrease in the partial pressure of O2 stimulates the chemoreceptors in the aortic arch in the carotids, and this leads to the tidal volume will increase for several hours, even days afterwards. As well, because of this, the pulmonary ventilation increasing, we have an increase in ventilation at altitude, which leads to something called hyperventilation, where we're breathing more, and as such, we're blowing off more CO2. So we're expiring more CO2, and as a result, there's a direct relationship between how much CO2 you have in your body and your pH. So if you're blowing off more CO2, the pH of your blood will rise and you become more alkalotic, and it leads to something called respiratory alkalosis. Okay, your pH in your blood is increasing beyond a pH of 7 or 6.8 to 7, which is homeostasis. You're actually blowing off more CO2, and therefore you're increasing your blood pH. As I mentioned on the previous slide, because at altitude there's an increase in ventilation, hyperventilation, you're actually blowing off more carbon dioxide. And CO2 in the body and hydrogen ion concentration are related, such that the more CO2 you have, the higher amount of hydrogen ions produced and the lower the blood pH. So as we've learned in biochemistry, a byproduct of metabolism is the production of CO2. And so with CO2, we also see an increase in hydrogen ion concentration within the body, which decreases the blood pH. And so with altitude, the opposite is true, such that we're blowing more CO2 off in our ventilation. And this increases our pH, making it more alkaline. So remember, we're blowing off more CO2. We have less CO2 in the blood, and therefore our blood pH is going to rise. And as a result of this, the kidneys excrete more bicarbonate, which we mentioned earlier that bicarbonate is one of our internal to the body are buffering systems. So this minimizes the blood buffering capacity, and you're peeing out more bicarbonate, and hopefully this will restore your pH from a high level back down to a pH of around 6.8 to 7, which is our normal level, our homeostatic level. Remember, we have an optimal level or a homeostatic level in our body for everything. And so the body has regulators in order to try to get back to the best possible situation for things to properly function. Next, we're going to talk about the impact of acute altitude exposure on oxygen transport. As we have already established, upon arrival to altitude, we see a drop or a decrease in alveolar partial pressure of oxygen. And as such, we cannot fully load hemoglobin with oxygen. We just don't have that driving force. We don't have a big enough pressure gradient to drive oxygen to bind with hemoglobin. And so what we see is a decrease in the hemoglobin saturation with oxygen. And this is exemplified in our oxyhemoglobin dissociation curve. We see a leftward shift. What we see, the typical curve is in this figure in red, and we see the blue figure indicating the leftward shift. So the shape and curve, shape and shift of the curve minimizes desaturation. I really enjoy this figure because it provides a step-by-step look at the changes in the partial pressure of oxygen throughout various spots of extreme importance in the body. So the left-hand side looks at sea level and the normal partial pressure within a human at rest. And then we see on the right an altitude of 4,300 meters and a barometric pressure of 460 millimeters of mercury, and how that changes the driving force for oxygen to get into the body. So let's look on the left-hand side first of all. And I want you to remember that a pressure gradient provides the driving force for oxygen to move. The greater the difference across tissues, the faster the diffusion. Okay, so on the left-hand side at sea level, we see in the alveoli, we see a partial pressure of oxygen of 159 millimeters of mercury. Then we see in the blood, it's around 100. So we have this driving force. There's a high concentration or high pressure within the alveoli, and this drives the oxygen into the capillary, into the blood. Okay, but I want you to see the real impact. It's down at diffusion that happens, or the gas exchange that happens at the skeletal muscle. So the diffusion gradient is 100 in the arterial blood, and in the skeletal muscle, the partial pressure of oxygen is 40. So we see a diffusion gradient of 60 millimeters of mercury at rest at sea level. Now let's look on the right-hand side. Let's look at the tissue, so the skeletal muscle. We see the diffusion gradient has significantly decreased, such that the partial pressure of oxygen in the arterial system is only 42 millimeters of mercury. Meanwhile, in the skeletal muscle, it's 27. So the diffusion gradient would only be 15 millimeters of mercury. Now, this is a massive difference, and this will significantly compromise the ability of the skeletal muscle to generate energy, because now we don't have oxygen diffusing and not in the mitochondria at the rate that we need. And so the body is forced to slow down so that the supply can equal the demand. So in your PowerPoint slides, you can right-click on this image and then choose Open Hyperlink to play this video. And it will help you understand the impact of altitude on changing the diffusion gradients in different areas within the body. As I am a visual learner, I find these types of videos really help solidify my understanding and all the theory that I'm talking about. So this slide is really basically putting into words what I explained on the previous slides. That what we see at the skeletal muscle is also a decrease in gas exchange. And this is all due to the decreased partial pressure of O2 in the arterial system and in the capillary, and therefore there's not as much oxygen going from the capillary into the tissue, into the skeletal muscle. So at sea level, what we typically see between the arterial system and the skeletal muscle is a pressure gradient of 100 to 40, which means that the driving force is 60 millimeters of mercury as a diffusion gradient. At 43 or 4,300 meters of altitude, we see that the arterial partial pressure is decreased significantly to 42. We also see a decrease in the skeletal muscle or the tissue partial pressure of oxygen to 27, which makes the diffusion gradient drop to 15 millimeters of mercury. At 5,800 meters of altitude, we see even more of a decrease by 5 millimeters of mercury to 10 millimeters of mercury as a diffusion gradient from the arterial capillary into the skeletal muscle tissue. And as such, we see oxygen diffusion into the muscle is significantly reduced.